So today we're going to talk about simple harmonic motion and uniform circular motion. It's easy to think of the spring moving backwards and forwards and backwards and forwards again, traveling to some maximum A point, back to 0, and then to some negative A point. So if we have something moving in a circle like this, it is also moving in periodic motion. This on its side, it will also exhibit periodic motion, going to some maximum A value, back to the equilibrium point, and then to a minimum A point, back to the equilibrium, and so on. As this is traveling around, it has a periodic relationship. Therefore, its speed you can represent as v equals 2 pi times the amplitude divided by the time. So now here's a spring, and this spring is represented from going from the negative point to 0, or its equilibrium, to its maximum, and then all the way back. And we know that as this happens, potential energy is being stored, gets converted into kinetic energy, and then when it gets back to the equilibrium, it gets converted back into potential energy. And because of this relationship here, the equation would be the maximum potential energy, or 1/2 Ka squared, will equal 1/2 mb squared. And this v here, discussed about up here, correspond together because they are in a periodic relationship. You can tell that the x is at its equilibrium. It will be also at its maximum value. So there we can find the velocity of the equation by only moving the x back and forth and not having to deal with the y correspondent. So because the velocity is at its maximum speed when x is at its equilibrium, the velocity can only be in the x value. So we set these two equations to equal each other so we can figure out the period, which would be 1/2 Ka squared, or the maximum potential energy, is equal to 1/2 mv squared, or the maximum kinetic energy. Then we can cancel out the 1/2, and then we're left with A squared over V squared equals m over K, and then that can be simplified as to A over V is equal to the square root of m over K. So now that we found A over V, we come back to the equation for velocity over here, and when we rearrange our variables, we are left with V over A is equal to 2 pi t, which we found coming down here for t is equal to 2 pi root m over k, which is what we are left with in our equation, and this is how we can find the period, and it's also related because we have the mass of the object and we have our spring constant, which means we can find our period. So now to be able to find the frequency, we have to take the reciprocal of the time equation, which is 1 over the frequency. So frequency is going to equal 1 over time. And because we have already found out what t is in this equation, we just plug in F equals 1 over 2 pi root K over M. So now that we have this, we can relate it to omega, or the angular frequency, which is W equals 2 pi F, or omega equals 2 pi frequency. And because the 2 pi and the 1/2 2 pi will cancel out, we are left with omega equals the square root of K over M to find out what our frequency of the period would be.